We're now going to take a look at the quotient test. So let's first formulate the test. So the quotient test is formulated for positive series. So let's here assume if AK is bigger than 0. And here we're going to divide by AK. So we're assuming here it's strictly positive, such that, and now this is kind of like the root test, but there's a different condition now. So the limit we're writing now is k goes to infinity, AK plus 1 divided by AK. This guy has to be equal to Q. And here it's important that you get the AK plus 1 upstairs and the AK downstairs. And the plus 1 here is in the index. Okay, so I'm taking AK and then I'm taking the next guy here. And then there are 3 cases. And case 1, case 2, and case 3 are identical to the root test. So this gives us that the series converges. This gives us no conclusion. And this gives us that the guy diverges. And of course here I don't really care what the summation limits are. I'm starting somewhere and going to infinity. That's the important thing. So let's look at an example first. And actually let's take exactly the same example as in the film for the root test. Usually you can apply these to, it's appropriate to apply these guys to the same examples, more or less. In any case, let's now sum k squared divided by 2 to the k. These are now our AKs. And to apply the quotient tests, we consider the limit as k goes to infinity of now AK plus 1 divided by AK. So, and now, if you're not used to applying this test, things may look a bit scary, but there's a, let's bear with me for a moment here. So this looks like this, and then like this. So then we need to clean it up. And the thing here is, so usually in these typical examples, you should compare each term to himself, so to speak. So the things coming from this guy should be compared to the things coming from this guy, and likewise here. So now I'm putting him with him, and I'm putting the square outside of everything. And then this guy should be here, and that guy pops up here. So now this looks a bit more tidy. And inside of here, what can I do? Well, I can divide out this case and then get here like this. And what can I do here? Well, I can strike 2 to the k, so I'm getting a half here. Suddenly this is not so bad. I can move the half outside, and then I can actually move this limit inside of this square because x squared is a continuous function. So this jumps inside by the composition rule. And then I just have this thing left. Now 1 over k goes to 0, so this thing just goes to 1. So I'm here getting, well, I usually write it like this just to convince the reader I know how this thing acts, and I'm getting a half here. So the conclusion is, well, by quotient tests, the series converges, just like that. So let's now go through a proof in 2 steps, basically. Let's do an intuitive argument and then do a formal argument for one of these cases. So now let's look at an intuitive argument. So what do we know? Well, we know that AK plus 1 divided by AK is more or less the size Q for large K. What does this mean? Well, this means that AK plus 1 intuitively is more or less like Q AK. What does this give us? So this is not as straightforward as the root test. So the root test may look a bit more scary than the quotient test, but the root test is actually the easier one to prove. So here, since I'm in the intuitive style, let's ignore the fact that we're only having this for large K. Let's suppose that we have this for all K. Then I have this for k is equal to 0, which gives me a1 is more or less this. Then a2, so I'm just putting a 1 here now, is q a1, but a1 was q a0, so this is q times q a0 equals to q squared a0. And if I continue like this, I'll see that this thing here is like q to the third a0, and this thing here is like q to the fourth a0. And that AK is more or less like Q to the K A0. And of course, summing up terms like this, I'm getting that this thing here ought to be the same as A0, and then the sum of Q to the K. And if Q is strictly less than 1, this ought to converge. And if Q is strictly bigger than 1, this ought to diverge. And of course, if Q is equal to 1, this ought to diverge also. But notice that here we get no conclusion. This is an indication that when you turn such an argument into a proper proof, you cannot save the intuition for the case when Q is equal to 1. It actually breaks down, and you can find examples showing that there is no way it can hold. So you have both convergent and divergent infinite series that correspond to Q is equal to 1. I can say that two such guys are these. Both have q equals to 1 if you do the quotient test limit, but this diverges and this converges. And this will also give the q equal to 1 examples for the quotient or the root test. So let's see now how to turn this into a formal argument. And since we did this for q strictly smaller than 1 for the root test, let's do it for q strictly bigger than 1 here. And the q strictly bigger than 1 arguments, both for the quotient and root test, are easier than when q is strictly less than 1. It's because now we can actually use the divergence test instead of a comparison. So let's be slightly careful here. So for every epsilon bigger than 0, there exists n, such that when k has passed n, we get that ak plus 1 divided by ak minus q is strictly smaller than epsilon. If we open up the inequalities here, we get ak plus 1 divided by ak, smaller than q plus epsilon, and here q minus epsilon. I'm doing these steps more slowly in the limit comparison and root test films. And in case we end up at the same type of expression, now I have that q is strictly bigger than 1. So if I do my number line here, I have 1 here, and then q is here somewhere. Here, this distance I can express as q minus 1. So if I take half of it, this will be q minus 1 divided by 2. So if I do epsilon equals to this number here, then q minus epsilon will give me this, which is still strictly larger than 1. So I'm choosing here this epsilon to be q minus 1 divided by 2. I can keep track of both my inequalities here. This one will be for showing that this converges, but then I would need q strictly less than 1 and an epsilon making this still strictly less than 1. So let's just ignore this from this point on and instead focus on this, which will give me the divergence, because now q is strictly bigger than 1 and q minus epsilon will still be strictly bigger than 1. That's the point. So I'm getting here q minus q minus 1 divided by 2. I'm keeping this guy here. Computing this, I'm getting q halves plus a half. I can write this as q plus 1 divided by 2. And remember that since q is strictly bigger than 1, this is strictly bigger than 1 plus 1 divided by 2, which is strictly bigger than 1. And now, if I were on this side and wanted to prove convergence, I would need to do something like this. But now I only want to prove divergence. So now I can actually use this type of inequality here. So I'm getting 1 strictly smaller than this, and I multiply up, so I get here ak strictly smaller than this. What does this mean? Well, this means that sequence ak is strictly increasing. What does that mean? Well, notice in my assumption here that all my ak's are strictly bigger than 0. So this thing here is definitely bigger than a naught, which is strictly bigger than 0. But this means here that I have 0, here I have a naught somewhere, and all my ak's, well, they will be here, right? Strictly increasing. So in particular, the limit ak as k goes to infinity cannot be 0. This limit will be bigger than or equal to a naught. And hence, by divergence test, this thing here diverges. And we're done.